Welcome everyone to the lecture for today in fluid mechanics. So we are going to discuss now fluid pressure. So the scope of this video session is on intensity of pressure, pressure variation in a liquid, gauge pressure and absolute pressure, pressure head, instrument used to measure pressure, and manometers. As for our learning objectives, at the end of this session, students will be able to define pressure, distinguish gauge pressure and absolute pressure, apply the formula in pressure and pressure head, relate to various instruments to measure pressure, relate with the units involved in pressure, solve problems involving pressure. So let us first define what is pressure. So it is defined as a normal force exerted by a fluid per unit area. So the units of pressure are in Newton per square meter, which is called a Pascal. Since the unit Pascal is too small for pressures encountered in practice, kilopascal, 1 kilopascal is equal to 1000 Pascal, and megapascal, 1 megapascal is equal to 1 million pascals, are normally used. Other units include bar, ATM, kilogram force per square centimeter, and pound force per square inch or PSI. So those are in English units. Pressure is the force per unit area, where the force is perpendicular to area. We can see here in the equation that P is equal to F all over A, wherein the force will be in terms of Newton and the area will be in terms of square meter. In terms of pounds per square inch, that would be equivalent to 6,895 Pascal. This is the absolute pressure, the pressure compared to a vacuum. The pressure measured in your tires is the gauge pressure, which is the difference between the pressure and the absolute pressure. Pressure in a fluid acts equally in all directions. This is actually the Pascal law. Pressure in a static liquid increases linearly with depth. So the equation goes pressure increase delta P is equal to rho G. And remember that rho G is actually the gamma or the unit weight. So this unit weight will be multiplied to the change in height or increase in depth in meters. The pressure at a given depth in a continuous static body of liquid is constant. So in here, we are always referring to the vertical height, wherein if the points are at the same level, the pressure would be equal. Hence, P1 is equal to P2 would be also equal to P3. Rho G here is the gamma. So pressure is the ratio of force to the area over which it is applied. Again, the formula goes with force all over the area. So if we have here a cross-sectional area equivalent to 2 square centimeter with an applied load of 1.5 kilograms, we can say that force all over area is the pressure equivalent to 1.5 kilogram times acceleration due to gravity divided by the cross-sectional area of the setup. Hence, we can come up with 73,500 Newton per square meter. Now, this term is actually derived from the formula of the weight, which is considered as force, equivalent to mass times acceleration due to gravity. The unit of pressure is in Pascal. A pressure of 1 Pascal is defined as a force of 1 Newton applied to an area of 1 square meter. Hence, 1 Pascal is equal to 1 Newton per square meter. In the previous example, the pressure was 73,500 Newton per square meter. This should be expressed as the pressure is equivalent to 73,500 pascals. As for the pressure head, the pressure in the area is static pressure of system. It is a column of water supported by this pressure. Hence, pressure head can be denoted by H equivalent to the pressure all over unit weight gamma. So, solving for pressure, we can say that pressure is equal to gamma H. Going upwards, we will be having a negative gauge pressure. And going downwards, your pressure will be in positive terms. Now, the fluid pressure is that fluids exert pressure in all directions. So, consider here an element that is submerged in a fluid. We can see here that the pressure are present in all directions. Fluid exerts forces in many directions. Let us just try to submerge a rubber ball in water to see that an upward force acts on the ball. In here, we compare the pressure versus that of the depth of the liquid. Again, we consider an element below the fluid, say H. So that H will have its corresponding mass and acceleration due to gravity that would yield to the weight of that element with the corresponding area. So the law of Pascal says that pressure at any point in a fluid is directly proportional to the density of the fluid and to the depth in the fluid. Again, pressure is equal to force all over area, wherein the force would be expressed in mass times acceleration due to gravity, and then the mass will be in terms of density. Mass is equal to rho times volume, and the volume will be in terms of area times the height, so that we can cancel the area, and therefore pressure is equal to gamma H, or that is density times acceleration due to gravity times the pressure head H. So pressure is independence of shape and area. Water seeks its own level, indicating that fluid pressure is dependent of area and shape of its container. At any depth h below the surface of the water in any column, the pressure P is the same. The shape and the area are not the factors. Therefore, we always consider that h is a vertical dimension. The properties of fluid pressure are: first, the forces exerted by a fluid on the walls of its container are always perpendicular. The fluid pressure is directly proportional to the depth of the fluid and to its density. And then at any particular depth, the fluid pressure is the same in all directions. Fluid pressure is independent of the shape or area of its container. Let us consider here an example. When a diver is located at 20 meters below the surface of a lake, wherein the density of that lake is equal to 1,000 kg per cubic meter. What is the pressure due to water? Hence, we have here the illustration wherein the diver has ahead from the liquid surface of H. The difference in pressure from the top of the lake to the diver is the pressure is equal to gamma H or rho g H, wherein the height is 20 meter and the acceleration due to gravity is 9.81 meter per second squared. So, substituting the values, we have 1000 times 9.81 times 20 meters. Hence, we can come up with the change in pressure equivalent to 196 kilopascals. Moving on to atmospheric pressure. One way to measure atmospheric pressure is to fill a test tube with the mercury and then invert it into a ball of mercury. We can generate a head here from that experiment. Recall that the density of mercury is equal to 13,600 kg per cubic meter. And that is derived from the formula of density in terms of the specific gravity. That is specific gravity times rho of the standard substance, which is water. We know that S of mercury is equal to 13.6 and the rho for fresh water is equal to 1000 kg per cubic meter. Atmospheric pressure is equal to rho gh, and we can derive here a head of 0.76 meters from this formula. The atmospheric pressure will be equal to 101,300 pascals, or that is, to be exact, 101.325 kilopascals. Hence, this will be considered as the values for atmospheric pressure. We have 101.325 kilopascals, 14.7 psi, and 760 millimeters of mercury. So moving on to the Pascal's law. So Pascal's law, an external pressure applied to an enclosed fluid is transmitted uniformly throughout the volume of the liquid. If we have here two pistons of different radius, pressure in is equal to pressure out. Applying the formula of pressure, force over area in both sides of the equation, we can come up with the equation force in all over area of the internal. That will be equal to force of the output all over area of the output. They are in the same level. Therefore, the pressure, the same fluid with the same level, the pressure will be equal. Considering this third example, the smaller and larger pistons of a hydraulic press have diameter of 4 cm and 12 cm. What input force is required to lift a 4,000 Newton weight with the input piston, with the output piston? So here's the illustration wherein the input force is to lift the 4,000 Newton weight. The radius of that piston is set to be equal to 2 centimeters, and the radius for the output force piston equates to larger one, 6 centimeter. We apply this formula. Force all over area of the input force is equal to force all over area of the output force. Solving for the input force, we can come up with that equation. Force output times area of the input all over area of the output. The area here refers to the cross-sectional area of the piston to that of the liquid. Radius, having radius equivalent to the half of the diameter, we can use that area is equal to pi r squared. Now, the force input can be derived by the equation, and substituting the value, the output force is actually 4,000. So 4,000 Newton is the weight to be lifted, and the area of the piston on the input side is pi r squared, that is pi times 2 centimeters squared, all over the cross-sectional area of the pressure on the output side, that is pi times 6 squared. So therefore, the required force to lift the 4,000 Newton is equivalent to 444 Newtons. Moving on to the relationship between the absolute, the gauge, and the vacuum pressures, we have a situation wherein at certain point, the absolute pressure is less than the atmospheric pressure. So it is understood that there will be a vacuum pressure to complete the level of the atmospheric pressure. And the atmospheric pressure is equal to 14.7 psi, 101.325 kilopascal, or that is 760 millimeter of mercury. So from this diagram, we can derive the pressure due to vacuum, that is equal to the atmospheric pressure minus the absolute pressure. Another situation on the right portion here is that the atmospheric pressure or the absolute pressure is greater than that of the atmospheric pressure. Therefore, from that diagram, we can derive that absolute pressure is equal to the atmospheric pressure plus or minus gauge pressure. So we denote a negative value for a pressure that is going upwards. As we write the equation, as we go upwards, we denote that by negative. While if we write the equation going downwards, we should denote it by positive. We note here that atmospheric pressure if the liquid is open and exposed to the Earth's atmosphere, while that vacuum pressure is a suction pressure. So a suction pressure, the very good example of this one is the vacuum cleaner, wherein instead of bursting pressure, the pressure is suction. Now, if we are working with gauge pressure, the pressure is 0 for liquid surface that is exposed to the atmosphere. So to summarize this, actual pressure at a given point is called the absolute pressure. Most pressure measuring devices are calibrated to read 0 in the atmosphere and therefore indicate gauge pressure. So gauge pressure is equal to absolute pressure minus the atmospheric pressure. The pressure below atmospheric pressure are called vacuum pressure. Hence, we can have vacuum pressure is equal to atmospheric pressure minus absolute pressure. With regards to absolute pressure, it is the sum of the pressure due to a fluid and the pressure due to the atmosphere. The gauge pressure is the difference between the absolute pressure and the pressure due to the atmosphere. Therefore, absolute pressure is equal to gauge pressure plus the atmospheric pressure. If we have a diver underneath a liquid, the liquid surface is set to be 101.325 kilopascal at that level. Therefore, the change in pressure is the gauge pressure actually equal to 196 kilopascal. And we know that 1 atmospheric pressure is 101.325 kilopascal. We simply add that one to come up with the absolute pressure. So pressure at a point, pressure at any point is in a fluid is the same in all directions. Pressure has a magnitude but not a specific direction, and thus it is a scalar quantity. A good example is that scuba diving and hydrostatic pressure. So the pressure here could be upwards, downwards, diagonal, or any direction. So pressure is present towards the diver at any direction. So pressure can be measured out of some instruments. It is an important variable in fluid mechanics. Many instruments have been devised for its measurement. Many devices are based on hydrostatics, such as barometers and manometers, like determine pressure through measurement of a column of a liquid using the pressure variation with elevation equation for an incompressible fluid. So here is a diagram or illustration of a differential manometer. In a differential manometer, the tube is tapped into the pipe so that we can determine the change in pressure. So again, pressure is force exerted on a unit area. It is measured in kilopascal or megapascal. And then atmospheric pressure at sea level is 1 atmosphere, 760 mm of mercury, and 101.325 kilopascal. In outer space, the pressure is essentially zero. The pressure in a vacuum is called the absolute zero. All pressures referenced with respect to this zero pressure are termed as absolute pressures. Many pressure measuring devices measure not absolute pressure, but only the difference in pressure. This type of pressure reading is called the gauge pressure. Whenever atmospheric pressure is used as a reference, the possibility exists that the pressure thus measured can be either positive or negative. Negative gauge pressure are also termed as vacuum pressures. So as one example of the instrument to measure pressure, we have several types of manometer. First, we have a U-tube wherein we can measure the column difference on both sides of the tube. So the U-tube can also be an inverted U-tube. Another manometer is an enlarged leg wherein we have a column of liquids from the reservoir and a column pipe. We also have here two fluid with two reservoir and a U-tube attached to it. And then an inclined tube tapped into a reservoir. So here is an example of manometer wherein we have here a gas on the reservoir and then the manometer is tapped wherein one end is exposed to atmosphere. So as a general rule, at points where we have the same liquid with the same elevation, we can say that the pressure are equal. Hence, P1 is equal to P2. And pressure at 2 can be written as the atmospheric pressure going down tayo, and then that would be equal to gamma H plus gamma H. An elevation change of delta Z in a fluid at rest corresponds to delta P all over rho G. A device based on this is called manometer. A manometer consists of a U-tube containing one or more fluids such as mercury, water, alcohol, or oil. In terms of large pressure, heavy fluids like mercury are used. We also have here multi-fluid manometer. So simply, there will be a multi-fluid or various fluids in a certain reservoir. Of course, heads of that various fluid will be measured. And then it is also applicable to a reservoir and a manometer tap into it. For multi-fluid systems, pressure change across a fluid column of height h is P is equal to rho GH or gamma H. Pressure increases downward and decreases upward. 2 points at the same elevation in a continuous fluid are at the same pressure. Pressure can be determined by adding and subtracting rho GH or gamma H terms. So here's an equation on the lower figure wherein the pressure equation was written starting at point 2. So to best illustrate this, let us have this figure with series of fluid. Writing pressure equation considering the gauge pressure is just the sum of pressures is equal to the end pressure. Now, if this point is point A, starting at point A, we write equations considering that if we go down, that will be indicated as positive, and if we go up, that will be indicated as negative. Now, since point A here is the topmost point of the setup, all of our operations will be in positive because we are all going downwards. So we start to write pressure at A and then go downwards plus pressure at fluid 1, and then from that we go downwards again, adding the pressure of fluid 2, and then from that level we further go down, adding the pressure due to fluid 3, and the end pressure is at the level of that point 1. We apply this equation that P is equal to gamma H. We just replace the corresponding pressures of fluid 1, 2, and 3 with that expression gamma H. So therefore, the equation will be PA plus gamma H of fluid 1 plus gamma H of fluid 2 plus gamma H of fluid 3 is equal to the end pressure, which is P1. So as an alternate solution, let us start at point 1. Remember that we are now going upwards. So the first pressure to be written is P1. We go up and then we less the pressure of fluid 3 since we are going upwards. And then we further go up to that level of fluid 2. We subtract that pressure of fluid 2, and then finally subtract the pressure due to fluid 1 until we reach the end pressure, which is the pressure at A. It is to be noted that pressure at A is exposed to the atmosphere, Hence, PA should be equal to 0. So another example here is a reservoir containing confined air on the reservoir and water on the main reservoir spilling down to the pipe with oil and mercury also. So each of those will have the head named as H1, H2, and H3. Writing pressure equation considering gauge pressure. Again, it is just the sum of the pressures is equal to end pressure. So starting to write the equation at point 2, considering that we have negative gamma H for going upwards direction and positive gamma H if we go a downwards direction. So from point 2, it is expected that we are going downwards until we can reach point 1. So the equation is from point 2, that is pressure 2, plus gamma H of mercury times the head of that mercury, H3. So at this level, we can denote this by a variable, say Z. So we go down, that is a positive gamma times Z of that mercury. And eventually, we will also have the same expression but oppositely directed. So in that case, reflecting that into the equation, that is cancelled. And then as we go up, going upwards direction, we'll have to deduct or subtract the next height and the liquid. And the liquid with that elevation is the oil. So we deduct negative gamma oil times H2. So it is within that level now. So the third stage, if we label that as H1, as in the figure, we will just have to deduct again since we are going upwards. See the involved fluid. The involved fluid is oil with the corresponding H of H1. Again, that is denoted by negative since we are going upwards. So from that level, we have now our arrow going up. Okay. So that corresponds to negative gamma of oil times X if this dimension is labeled as X. And consequently, again, we have the same expression with different sign, reflecting that into the equation. Again, that will be cancelled. So notice that here, we can cancel this term because of the same principle that H1 and X have the same liquid with the same elevation. And then from this level, we will go down until that mouth of the top manometer that is going downwards, and then eventually it will have the same gamma H for going upwards to reach that level. We are now inside the reservoir until we reach point 1. Lastly, we'll consider an upward pressure direction with water and H1 as its corresponding head. Hence, we are going to have negative gamma water times H1. and then the end pressure finally is equal to P1. Again, we will find that P2 is equal to 0 since it is exposed to atmosphere. So basically, the key concepts here are as follows. We use the formula that pressure is equal to gamma H. Gamma H could be expressed into positive if it is going downwards and negative if it is going upwards. Same level, same liquid has the same value of pressure. And then along the way, on the problems, we should recall that gamma is equal to specific gravity times gamma of the standard substance, which in the fluid is water. And then finally, pressure is 0 at liquid exposed to the atmosphere. So the concept of measuring pressure drops is again computation of pressure. Manometers are well suited to measure pressure drops across valves, pipes, heat exchangers, and the like. Relation for pressure drop P1 minus P2 is obtained by starting at point 1 and adding or subtracting gamma H in terms until we reach point 2. If fluid in pipe is a gas, therefore, the density of 2 is far greater than density of the fluid 1, and P1 minus P2 is equal to gamma H or rho GH. So the barometer is another instrument to measure pressure. Again, this was demonstrated a while ago, wherein an inverted test tube is filled with mercury and then invert it to the reservoir. So the fluid element will have the weight equal to rho GH times the cross-sectional area. So the atmospheric pressure is the exposed liquid level. Hence, PC or the inside pressure, the confined pressure inside the test tube, will be added to gamma H, and that would equate to the atmospheric pressure. Atmospheric pressure is measured by a device called a barometer. Thus, atmospheric pressure is often referred to as the barometric pressure. Now, the confined pressure PC can be taken to be 0 since there is only mercury vapor above point C and it is very low relative to the atmosphere. Change in atmospheric pressure due to elevation has many effects. Like in cooking, we use the pressure cooker. Too much pressure will cause us nosebleeds. And then the engine performance overheating can be observed with the high pressure on our radiator. That is also true to aircraft performance, wherein a pressure could also boost up the speed of our aircraft. So measuring pressure through manometers. Again, the concept here is just summing up pressures or pressure head that is vertical. So the manometer is more on measuring gauge pressures. So if we have here a manometer with one open side, meaning the pressure at Z is exposed to the atmosphere. So therefore, considering the gauge pressure, that will be equal to 0. And if we are concerned with the absolute pressure, the pressure at Z is actually 101.325 kilopascals. So in this case, P1 is equal to Px, considering that our fluid on the pipe is a gas. Remember that gas has substantially smaller than that of the liquid. So therefore, the pressure that would be generated out of that tube will be negligible. So therefore, P1 would be equal to Px. So take note that the negligible pressure can only be applied if we have a gas element inside the tube. And now, Px is equal to Py since they are in the same elevation with the same liquid. We can also say that Pz is equal to P2 is equal to the atmospheric pressure since it is open. From this, we can derive P1 minus Pz is equal to gamma h, or P1 minus Pa is equal to gamma h. So that ends our lecture for the pressure, and we are now ready to have examples